Okay, we're going to look at these inconsistent and dependent equations. So the first one, number 1, we have this little system of 2 equations. It wants us to use Gaussian elimination. So in order to use elimination, we need to set up our augmented matrix. We have 2, 5, 4, 10, 10, 10. And so Gaussian elimination, remember that our goal is to get the diagonal of 1s and 0 below, and then any number there. And so then we can do back substitution to solve. Okay, so I don't see a 1 being made really easily, but I do see that I could make this 4 turn into a 0 if I take negative 2 times row 1, add that to row 2, that would make my new row 2. So what that would look like is my scratch work here. Negative 2 times row 1 would be negative 4, negative 10, negative 20, and then we add row 2 to that, that's 4, 10, 10, and so I'm going to get 0, 0, negative 10. So my matrix, again, my first row is not changing, 2, 5, 10, but my bottom row would become 0, 0, and negative 10. So if you look at it, I'm trying to put it into that form, but I can't get that 1 in that other spot because that 0 is going on. If you want to see the 1 in that first one, we could take half of row 1 to make my new row 1. If you want to see that, it would be 1, 5 halves, and 5, and then we'd still have 0, 0, negative 10. So that's as close as we can get to what our goal was. And so you notice that if we rewrite this as our system, it's x plus 5 over 2y equals 5, and we get 0 equals negative 10, which will mean we have no solution here. And so now I'm going to look at the graphs of those two guys. So the first one, 2x plus 5y equals 10. A couple different ways to graph that. I'm going to put it in our nice y equals mx plus b form. Make this a little bigger here. So minus 2x, we get 5y equals negative 2x plus 10. Divide by 5. We get y equals negative 2 over 5x plus 2. So if I want to graph this line, my y-intercept is 2, and my slope is negative 2/5. So I'm going to go up to 2, that's my y-intercept. Then down 2 spaces, run 5 spaces to follow that slope. And so the sketch of that line I have there. Now the other equation, that one is, go back up, 4x plus 10y equals 10. So if we do the same thing, put it in that form, y equals mx plus b minus 4x, we get 10y equals negative 4x plus 10. Divide by 10. We're going to end up that y will equal, well, negative 4/10 reduces to negative 2/5 x. We also need the 10 over 10 though, and that would become a 1. So we're going to go up to 1, and then from there our slope will go down to over 5. So it actually has the same exact slope as the first line I drew. And so that means these two lines are parallel. So the graphs, they don't intersect since they have the same slope and are parallel. Which you can see. And if they don't intersect, then there will be no solution to this. So one way to write no solution is that 0 with a line through it, or you can write the little curly braces to say a set with nothing in it, or we can just write in words, there is no solution like we expected. All right, let's look at number 2. Looks really similar to what we just saw over here, except they have a 20 instead of a 10. So let's see how that affects things. So I'm going to go back to my augmented matrix and write 2, 5, 4, 10, 10, and 20 this time. And again, it's kind of hard to make a 1 without getting some fractions. That's what I see anyway. But to make that 4 turn into a 0, I can do the same row operation on the last problem. So negative 2 times row 1 plus row 2 to make my new row 2. So again, it's going to be a -4, -10, -20. But now row 2 is 4, 10, and 20. So what's going to happen is I'm going to get all zeros. So my first row, 2, 5, 10 is there still, but I'm going to get all zeros down below. Again, if you really want to make that 2 turn into a 1, we could take half of row 1 to make my new row 1. So it'll be 1, 5 halves, 2, and then 0, 0, 0. But you can see this last step right here is 0 equals 0. This is true. And so we know that we're going to have infinite solutions. And again, that top line here, that's x plus 5 over 2y equals 2. Well, actually not 2. That shouldn't have been 2. That's dividing by 2. That should actually be 5. Let me go back. Fix that. That should be 5. So then this should be 2, not 2 anymore, but actually a 5. So x plus 5 over 2y equals 5. So now we graph the solution. What does that mean? We're going to have infinite solutions. Well, my equations, I already know that 2x plus 5y equals 10. That's y equals -2/5 x plus 2. So sketching that again, we're up at 2, down 2 over 5, puts us here. So you can see again, that's the same line that we had on the previous problem. And the second equation changed just a little bit. That's 4x plus 10y equals 20. So now we're still subtract 4x. We have 10y equals -4x plus 20 this time. So when we divide by 10, we end up that y equals -2/5 x plus 2, which is identical to the equation of the line we just made. So if I were to plot it and ignoring things, it's going to do exactly the same thing. And so every single point is going to satisfy both equations. So where do they intersect? All over, which is what we would expect when we see infinite solutions there. And so our solution set, there's a few different ways that you can write it. We can write it, since it's the same line, we can just say that it's all the x and y as long as they satisfy, and I'm just writing the first equation down, 2x plus 5y equals 10. So that's one way to write it. We can also write it as an ordered triple where we say, okay, well, x can be anything, but you can see here's an expression for y. So that's -2/5 x plus 2, and we could say that x is a real number. Either way would be fine here. Okay, flipping the page for number 3, it wants us to determine the number of solutions and the solution set. So if I want to rewrite this first, the first equation would be x plus 2y equals 5, and the second one would be 0x, so we just have 1y equals 0. So for this one, I actually have a y value that's 0, so I could plug it in here, and that would get x plus 2 times 0 equals 5, so that would tell me x equals 5. So I actually have one solution here. I know that you see two things, but this is an x and a y. That's the ordered pair. So my solution set would just be the ordered pair 5, 0. That is still just one solution, even though you see x and y. For part 2, it looks really similar, except the second equation. So let me write the first, x plus 2y equals 5. The second equation would be 0 equals 0. Again, this is infinite solutions. So we know that it is, in this case, a line on top of another line. So the number of solutions, we have infinite. And then what do the solutions look like? Again, like the last page, there's a few different ways you can write that. When I look up here, it looks like it's really easy to solve for x. So I'm going to say x equals 5 minus 2y. So I'm going to say that it's all the ordered pairs where my x's look like 5 minus 2y. My y's can be any real number, though. So if you knew what y is, you could figure out the corresponding x. And we could write it in a set. Alrighty, for part C, we have x plus 2y equals 5, and then we get 0 equals 1. Well, that's not true, so we know that there are no solutions, so we could say 0. Let me write that a little better. So when it says number of solutions, there are 0 solutions, because nothing will work. And the solution set, we could again write the set notation with nothing in it, or you could write a 0 with a line through it. Those are both empty sets. All right, for number 4, determine the solution set for the system represented by each augmented matrix. Okay, so again, it's just asking us to rewrite these back into the equations. So we have x plus 6z this time, right? Because x, y, z equals 2. We have y plus 4z equals 5. And then we have that z equals 0. So this is not a no solution one because we actually do have a value for z. Z is 0. So we're going to use back substitution. So I'm going to plug this into the second equation. So that will be y plus 4 times 0 equals 5. So that's just y equals 5. So we have a y value. And then on the top equation, we actually just need to plug in z again because there's no y. So we'll get x plus 6 times 0 equals 2. That's x equals 2. So my solution would be the ordered triplet x, y, z. That's my solution. For part B, let's write that system out. We'll have x plus 6z equals 2, y plus 4z equals 5, and then 0 equals 1. So as soon as we get something false with no variables, we'll say that there's no solution to this. For part C, we end up that x plus 6z equals 2 and y plus 4z equals 5, and then we have 0 equals 0. So right here, since this is true, we know that there's infinite solutions, but we want to know a little bit more. What does it look like? Well, one way to do that is to say, okay, well, let's let z be any real number. So we're going to be an ordered triple where z is any number. And let's look up above and see if we can solve for x and y in terms of z. So right here, if I want to get y alone, I could minus the 4z, so I could say y equals 5 minus 4z. So this is an expression for y that's made up of the z's. So 5 minus 4z. And then similarly with the x's, if I move the 6z over, it ends up that x is equal to 2 minus 6z. So I just wrote an expression for x using only z. So I'm going to write that as my x value, 2 minus 6z. And so this right here shows me an infinite number of solutions, and it's all the ordered triples that will satisfy both the top two equations. And that will be where those planes are intersecting. All right. We have a 3 by 3 system now. I'm going to write the augmented matrix for that. We'll have 1, -3, 14, -9, -2, 7, -31, 21. And again, this is just the coefficients in here, no variables, but they are in line with their variables. So make sure that there's no tricks going on. These are all x's in the first column, y's, z's, perfect. So this is my augmented matrix. So now remember what my goal is. We need to have, it says Gaussian or Gauss-Jordan elimination, but we want the diagonal of ones with zeros below, and then we could decide if you want to change those numbers to 0 or what. So this is our goal. So I have the 1 right away, yay. So I just need a -2 now to turn into a 0. So if I multiply 2 times row 1, add that to row 2, that could make my new row 2. So all my other ones will stay the same. Let's see, 1, -3, 14, -9, 1, -5, 20, -14. So I need to do this little side work. You could again do it in your head, but I'll write it out for you. So it has negative, or 2 times row 1, so that's 2, -6, 28, -18. And then row 2 is -2, 7, -31, 21. So combining those, we'll get a 0, a 1, a -3, and a 3. So we'll rewrite that, 0, 1, -3, and 3. So we got the 0 we needed. So next, we'll want to make that 1 into a 0. So we could just take row 2 minus row 1, or sorry, row 3, and that will make my new row 3. So again, row 1 and row 2 are going to stay the same this time. So 1, -3, 14, -9, 0, 1, negative 3, 3. But my little side work, row 3 is 1, negative 5, 20, negative 14. Subtracting row 1, that's 1, negative 3, 14, negative 9. We get, subtracting, hold on, I didn't change my signs. So this was row 3, and then we need a minus row 1. So that would change all these signs. So negative, negative, and positive. So we get 0, negative 2, 6, and negative 5. So let's plug that in here. 0, negative 2, 6, and negative 5. So I have my 1 with my zeros below. I have a 1 already starting at my diagonal. So I need the negative 2 to turn into a 0. So that's going to be, let's do negative 2 to go away needs a 2. So 2 times row 2 plus row 3 will make my new row 3. So I'm going to keep everything else the same. So row 1 is still 1, negative 3, 14, negative 9. Row 2 is 0, 1, negative 3, 3. And now row 3, well, we could do our little side work. 2 times row 2. 2 times row 2 is going to be, let's do my little side work up here. 0, 2, negative 6, 6. Row 3 is 0, negative 2, 6, negative 5. So we're going to get 0, 0, 0, 1. 0, 0, 0, 1. And as soon as I cancel out all those variables, you can see right here, I get 0 equals 1, which is not a true statement. And so we don't have to go any further. We're just going to say there is no solution to this system.